Hello everyone, welcome to the 10th episode of the series. In this video, we'll talk about computing matrix inverses. So in the last episode, we learned about matrix inverses. We learned that matrix inverses were unique whenever they existed and that they allowed us to rearrange matrix equations and solve for linear systems. In this episode, we're going to introduce an algorithm to check invertibility and to compute inverses. And we are also going to poke at the connection between invertibility and rank. Okay, so we're going to start with the easiest of the cases, a 2 by 2 matrix. So assume that we have a 2 by 2 matrix given by entries A, B, C, D. If the quantity AD minus BC is non-zero, so we multiply A and D and B and C and then take the difference and that is non-zero, then A is invertible and A inverse is given by 1 over AD minus BC times the matrix D minus B minus C A. Um, and one can verify that this A inverse times A is always identity and A times A inverse is also always identity. And if AD minus BC ends up being 0, then A is non-invertible. This quantity AD minus BC is called the determinant of the 2 by 2 matrix A. And we'll generalize determinants to all square matrices in the next episode. Okay, so let's look at an exercise. So we're given a matrix A with entries 1, 2, 3, 4, and we want to determine whether this is invertible. And if it is invertible, we want to compute its inverse using the formula that we saw on the last slide. So we first compute the determinant of the 2 by 2 matrix. We get 1 times 4 minus 2 times 3, that is minus 2, and that is not 0, and therefore A is invertible. In other words, A inverse exists. And we can compute the actual A inverse by the formula that we saw on the last slide, and that was 1 over AD minus BC times the matrix D minus B minus C minus A. We just plug in the entries for A, B, C, D, and we get that the inverse is minus 2, 1, 3 over 2, and minus half. Yeah, so the next thing we want to look at is an algorithm for finding the inverse of an n by n matrix. So in general, like how do we compute inverses, or how do we find a solution to the matrix equation Ax equal to D, where x is the variable matrix? So we're going to use elementary row operations. The first step is to write an augmented matrix A and concatenated with identity with a vertical separator line in the middle. And then we perform elementary row operations to transform this augmented matrix into a matrix in row echelon form. If this row echelon form has a leading one in every column left of the vertical line, we continue using row operations to further put it in the form identity A inverse. In other words, if it has leading one in every column on the left of the separator line, then we have to keep using row operations to convert this A eventually into an identity, and whatever matrix we have on the right side of the separator line would be our A inverse. And if it doesn't happen, then A is not invertible. So this method takes a lot of time, and over a period of this course, we're going to learn other ways to find A inverse. So let's look at another exercise. So we're given a 3 by 3 matrix, and we want to show that the inverse of this matrix does not exist. We're going to show that the inverse of this matrix does not exist by applying the algorithm that we described above. So we start by concatenating the given matrix and the 3 by 3 identity matrix with the separator line in between. And then we use row operations to try and convert this left-hand side into the identity matrix. So first, we multiply the first row by 2 and add it to the second row, and then we take the first row and add it to the third row. And this is what we end up getting. Then we take the second matrix and we subtract the second row from the third row, and we see that on the left side of the separator line, the third column has no leading one, and just going from the algorithm, we know that A has no inverse. So we can actually stop at this point, and we don't need to try and uh, like convert this into the identity matrix because we can't. Now let's look at an exercise where the matrix does exist. So we're going to find this inverse using the algorithm like in the previous problem. So we start by concatenating A and the 3 by 3 identity matrix. And then we are going to use row operations to convert this matrix on the left of the separator line into an identity matrix. So the first step we do is we switch out rows 1 and 2 with each other. And then um, we subtract 3 times row 1 from row 2 and 1 times row 1 from row 3. And once we have that, we subtract row 3 from row 2. And in the next step, we add row 2 to row 3. Then we divide the third row by 25 or multiply it by 1 over 25. And then because at this point we already have leading ones in each column, we know that the inverse does exist, so we can keep going forward. So we can use this last leading one to eliminate this -8 and -5. And once we are done with that, we will have the 3 by 3 identity matrix on the left of the separator line, and another 3 by 3 matrix on the right of the separator line. And this second matrix is going to be our A inverse. So the algorithm tells us that A inverse is 1 over 25 times 10, 0, minus 5, 1 minus 10, 7, and 3 minus 3, 5, 4. And for the sake of your sanity, you should take this A inverse and compute A times A inverse and A inverse times A to verify that it is indeed the inverse of the matrix A. Okay, so there's a powerful connection between invertibility and rank. An n by n matrix is invertible if and only if its rank is n. And why is that true? So when we start with the augmented matrix with A and identity, separated by a vertical line, we perform row operations to get to a row echelon form, given by some matrix B and C. Now, since B and C is in row echelon form, the matrix B is equivalent to the matrix A that we began with. And by definition, the rank of A is the number of leading ones in this row echelon form B. So the rank of A is the number of leading ones of the augmented matrix, B vertical line C, but only counting onto the left of the vertical line. Now, with this connection between invertibility and rank in mind, let's determine whether the following matrices are invertible without actually computing like the inverse. So the first matrix is a 4 by 4 matrix, and it's already in row echelon form because every row has a leading one. And since it's a 4 by 4 matrix, that gives us that rank is 4. And from the connection that we made between invertibility and rank, we know that this first matrix is invertible because it's a 4 by 4 matrix, and the rank is 4 as well. On the other hand, the second matrix, this is also a 4 by 4 matrix, and it's in row echelon form, but the rank of this matrix is only 3 because the last row does not have any leading ones. And therefore, this matrix is not invertible because the rank is less than the number of rows and the number of columns in this square matrix. Okay, so in this episode, we learned about computational algorithms to compute a matrix inverse. We saw that computing 2 by 2 inverses was easy, and computing larger inverses involves a lot of work. We also saw a connection between invertibility and rank. And with this, I would like to end this episode. I will see you guys soon. Until then, happy learning.